This is a little weird, so I'm sorry if it damages your brain. Try to wrap our heads around it. There's lots more donuts, so if that helps, come get some more donuts. Otherwise, I'll just eat them all and feel terrible about myself. So this valence bond theory stuff works nicely for these relatively simple molecules, for things that are really predictable, like carbon-based molecules. But there are a lot of instances where we get in trouble with valence bond theory, where it doesn't work. One of them we've already encountered, when you have odd-numbered electrons. So you have something like NO, and we want to, that's a real molecule that exists. We want to draw a Lewis structure for it. We count up that our electrons are 11. So we have a couple choices here. You know, we can put in a triple bond like that, but then there's one more electron on oxygen. That violates the octet rule on oxygen. We could put it, we can make a double bond, so at least we don't have more than an octet, but now we still violate the octet rule because we have less than an octet on oxygen. We can try to put that single one over here, but now we've got less than an octet on nitrogen. That also violates the octet rule. So if we've got all these violations of the octet rule, yet the molecule exists, how can that be? And the answer is that that rule, the octet rule, the basis of valence bond theory, just doesn't work well for for any molecule that has an odd number of electrons. So we need something better. It also doesn't explain some phenomena, like oxygen, for instance, O2, can be paramagnetic. We've talked about paramagnetism in atoms. If it has unpaired electrons, right, you can have a paramagnetic atom. But the Lewis structure for oxygen shows all the electrons being paired up. So how can oxygen as a molecule be paramagnetic if all of the electrons are paired up? And so again, we have a situation where the theory that we have just isn't explanatory enough. It doesn't explain what's going on in enough detail, and it has some exceptions. So we need a better theory, and the better theory is called molecular orbital theory. So remember when we do Lewis structures and we talked about all the electrons kind of going into a pot and then getting redistributed around all the atoms? Molecular orbital theory kind of works that way, but with orbitals. So we say, instead of individual orbitals on atoms that then connect together, the way we've drawn it here, we talk about molecular orbitals. So the basis for molecular orbital theory is atomic orbitals combine to form molecular orbitals. So in a molecule, instead of talking about the s orbital on this atom and the s orbital on this atom, we talk about the sigma orbital in this molecule. And so let's construct some molecular orbitals and see what that means. Let's look at a hydrogen molecule, dihydrogen. So we would say that in valence bond theory, that each hydrogen has a 1s orbital, and those two 1s orbitals combine to make the bond. In molecular orbital theory, we make two combinations, linear combinations of the atomic orbital, and we talk about adding them, and we talk about subtracting them. The subtracting gets a little weird, so let's talk about the adding first, because that makes sense. If we add those two together, we come up with a new orbital that looks like this, and is called the sigma 1s orbital. So that's not, even though we're using that same sigma, it's not a sigma bond, it's a sigma orbital, meaning that it's an orbital, a place where electrons can go, that goes over the entire molecule. In this case, it's just 2 atoms, but it goes over the entire molecule. So what does it mean when we subtract those then? Well, there's still wave functions, and we can still do these kinds of things. When we subtract them, we talk about destructive interference, and we end up having a 2-phase system that looks like this. What we've shown there is a node in the middle, just like a p orbital, a place where electrons can't go. So when you subtract 2 orbitals like that, you end up making that whole thing on the right is one thing, and that is called a sigma star orbital. So sigma with a little star. The one where they're combined, the one where they're additive, is called a bonding orbital. And the one where they're not is called an anti-bonding orbital. We're going to fill these things with electrons in a minute. So any electrons that take up bonding orbitals, we say, are forming bonds. They are bonding electrons. They are forming those connections. Any electrons that end up in anti-bonding orbitals we can say that they break bonds. So they cause the atoms to want to come apart. So putting electrons in a bonding molecular orbital is stabilizing to the molecule. Putting electrons in an anti-bonding orbital is destabilizing to a molecule. So we construct these in something called a molecular orbital diagram. And we'll do it just for hydrogen first because it's the simplest one, and then we'll progressively get more and more complex. So for the hydrogen molecular orbital, what you do is you put each atom on one side of your diagram and the molecule in the middle. So right now we're just going to focus on diatomic molecules, molecules with 2 atoms. You can do molecular orbital diagrams for any kind of molecules, but they get more complicated. And then we first put the orbitals on each side for the atoms that they're bringing to the molecule. So each hydrogen has a 1s orbital, and that's it. Our y-axis here, by the way, is energy. So the lower we draw an orbital, the lower energy or the more stable it is. The higher we draw an orbital, the higher energy it is. We put both of those 1s orbitals at the same spot because a hydrogen 1s orbital is always at the same energy no matter what atom it is. So now we're going to draw the combination of those 2 orbitals into molecular orbitals. As we talked about above, we're going to make 2 molecular orbitals out of our 2 atomic orbitals. And they're going to be different energies. Our sigma orbital is lower energy, our bonding orbital. And our sigma star orbital is higher energy. It's like a fun surprise all day. Yeah. So we've got our atomic orbitals on the outside, molecular orbitals in the middle. And then you don't have to, but we generally draw some sort of connecting lines showing that those came from these particular orbitals. And that will become more important when we have more orbitals. We want to know which ones are coming from where. All right, so we've got 1s atomic orbitals making sigma and sigma star molecular orbitals. The last step in the molecular orbital diagram is filling the electrons. So first, you can put the electrons on their atoms that they came with. So each hydrogen has 1 electron. And then you pool those electrons and build them from the bottom up in the molecular orbital diagram. So we've got 2 total electrons. We start at the bottom, 2 electrons per orbital, 1, 2. And that's our complete molecular orbital diagram. So what this is showing us is that the 2 electrons in the hydrogen molecule are both existing in a molecular orbital that's a sigma or bonding orbital. And this tells us that we have a bond in this molecule. So we use something called the bond order to figure this out. The bond order is the number of bonding electrons minus the number of antibonding electrons, all divided by 2. So for this molecule, there are 2 electrons in a bonding orbital. There are 0 electrons in an antibonding orbital. So we divide that by 2, and we get 1. And that tells us that we would expect or predict a single bond in the HH molecule. And in fact, that's what we see. So it's predictive in that way.
And is the molecular orbital theory like pretty much 100% like correct? Like in it?
The theory is correct. There are always strange situations, but that don't seem to work out nicely. But it's far more general. So you can adapt this to different situations and pretty much have it work, at least in some way.
Okay.
Yeah. So let's look at what happens when we do the same thing, but instead of hydrogen, we look at helium. So we're asking the question, does the helium-helium or He2 molecule exist? And one way to figure that out is to construct a molecular orbital diagram and see if it is energetically favorable to put these things together. So anytime you have the same types of orbitals, your molecular orbital diagram is going to look the same. So we can pretty quickly redraw this, knowing that anything made up of 1s orbitals is always going to have the same type of diagram. So where the orbitals go, what types of orbitals are formed, that pretty much stays the same. What changes is the number of electrons, because helium has 2 valence electrons instead of just 1. So we can put those in the molecular orbitals here. We got 4 electrons now. And when we calculate the bond order, we've got 2 minus 2 divided by 2, which is 0. And that tells us that we would predict the He2 molecule would not exist, because there's as many electrons in antibonding orbitals as in bonding orbitals. And that means that there's no energetic advantage for this molecule to be together.
So antibonding antibonding ones say that the electron will not bond with stuff. Bonding electron things say that it will bond.
The atoms will bond together,
Yeah.
right? Yeah. Eric, do you have that?
So the bonding order just has to be greater than 0 for it to exist.
Yes, although it gets a little bit more, we'll see, it gets a little bit more complicated than that. But in a lot of cases, yeah. Yeah.
Can you repeat like the order that you put in the electrons again?
You always go from the bottom up.
So like you go like 2 in the bottom and
Yep.
then to like the left.
No, the ones on the left and the right are from the atoms. So that's like, because a helium atom just by itself has 2 electrons in a 1s orbital. So those are the ones that it brings with it. And then what we fill up is the middle, which is the molecule.
So you would fill up the bottom entirely until it's full.
Until it's full.
If you have more electrons left over, you would have added to the top.
Right. And you keep kind of building that. All right, so we can keep doing this for bigger and bigger atoms. It looks pretty similar for lithium and beryllium. We just add another s orbital. So we'll skip those for now. We're going to jump over to the p block where it starts to get a little bit more complicated. Yeah. What about charges?
Like if it was an He -2.
Oh, that's a good question. So if there's charges, then you need to add or subtract that number of electrons. So like, well, you need a molecule, like for the whole molecule. So for your example, let's say we want to know if He2 exists. No. Does He2 2+ exist? Let's see. We can go back to our diagram here. And how would we change this for He2 2+? We would subtract 2 electrons. So we take these 2 electrons out of the top because that's the highest energy, so those are the ones that come out. And now what's our bond order? Is what? 1. So we would expect if you took 2 electrons out of that He2 molecule, then you would get a single bond between those two. And so you'd have kind of a polyatomic ion, He2 2+. Because the bond order is 1 there. I'm going to put these back in so it's not confusing, but for He2 2+, that would exist. We couldn't. It also tells us that we can't add electrons to He2 because there's no molecular orbitals for them to go into. So we couldn't have something like He2 2- or even 1- because those electrons are already full. Just looking at how the book does it, you'll notice if you go through there, if you're looking at the homework, they use blue and red to indicate the 2 phases. So when you've got an anti-bonding type orbital, you're going to have blue and red. All right, let's see where we're almost there. Let's look at boron. Actually, let's not look at boron. Let's look at oxygen. So we're going to start the same way. Constructing the molecular orbital diagram always works the same way. You put your atomic orbitals on the sides, and then you put your molecular orbitals in the middle. As we get to bigger molecules like oxygen, we just have more orbitals to deal with, but the technique is still the same. So what types of valence orbitals does oxygen have? Or what are the valence orbitals? What? An S?
Yeah, 2 S's.
It's the 2s, yep. So the 2s orbital is one of them. So we're going to put our oxygen atoms on each side again, our O2 molecule in the middle. Give yourself plenty of room here. So the lowest energy valence orbital that oxygen has is the 2s. What else does oxygen have? The 2p. And how many of those are there?
Well, there's 3.
3 orbitals. 3 orbitals. We'll get to the electrons in a minute. Oxygen has the 3 orbitals in the 2p, and they're all the same energy in the free atom.
Are we not caring about
They're all
the
degenerated.
1s?
No, we're not caring about the 1s. Why not?
It's like, it's the core electrons.
Yeah.
Wait, why?
It's not a valence electron. It's not the valence. We're only the valence electrons participate in the bonding, so we don't need to worry about the core electrons. All right, so we've got all of our orbitals. We might as well put our electrons in there too. How many valence electrons does oxygen have? 6. So we're going to go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 12 electrons overall in this molecule. Now to construct the molecular orbital diagram in the middle, we have to think about how orbitals can combine, how atomic orbitals can combine to make molecular orbitals. The bottom is the exact same as hydrogen. Two s orbitals, I mean, not the 2s, but two s orbitals, whether they're two 1s orbitals or two 2s orbitals, always combine the same way. We drew it up here. They're always going to make a bonding orbital like this and an anti-bonding orbital like this. So that's great. We can do the same thing we did before. We're going to make a bonding orbital that goes below and an anti-bonding orbital that goes above. And that's how s orbitals will always combine. Okay. Now the p orbitals. So this is where it gets a little bit tricky, because not only do we have 3 of them to deal with, but they're oriented in different ways, which means they're going to combine in different ways. Rather than try to draw all of that, especially because it gets difficult in 3 dimensions, we're just going to use pictures from the book here. So there are 3 ways that p orbitals can combine. I'm going to put these in the notes so you have them here. 3 ways that p orbitals can combine. That's one way. If the p orbitals are aligned right up against each other like that, they make sigma bonds. Sigma bonds are, we usually talk about p orbitals as making pi bonds, but if they're in the right orientation, they also make sigma bonds. So a sigma bonding orbital is going to look like that up below, and a sigma star anti-bonding orbital looks like that above. So we can add that to our molecular orbital diagram, that we're going to have a sigma orbital from the 2p and a sigma star from the 2p. So that takes care of one orbital on each side. Since those are the p orbitals that are oriented right against each other like this, that means the 2 other p orbitals are like this or like this. And so those are lined up parallel, and that tells you that they're going to do pi bonding instead of sigma bonding. So lobe to lobe, kind of on edge like that, is sigma bonding. If they're lined up parallel, that's what we call pi bonding. For the other 2 orbitals, are going to be like that. That's pi bonding and pi anti-bonding molecular orbitals, pi and pi star. And like this for the other direction, for the perpendicular ones. So you've got your sigma bonding p orbitals, and your pi bonding p orbitals, and that takes care of all 6 molecular orbitals. Now the sigma ones are, the bonding ones are lower in energy, and the anti-bonding ones are higher in energy. So we've already drawn those in. The 2 pi orbitals are degenerate, meaning they're the same energy. It doesn't matter if you're this way or this way, there's no effect on the energy there. So those orbitals are going to be the same energy, which means when we put them in here, we're going to draw them right next to each other. To show that there's 2 orbitals, the same energy. And then we'll connect these because all of these are coming from the p orbitals. Now we've constructed our complete molecular orbital diagram, and we can start filling it with electrons. We've got 12 total electrons, so we'll start from the bottom and work our way up. 1, 2, 3, 4, 5, 6, 7, 8. So we spread those out because those are the same energy, and just like when we're doing atoms, electrons would rather be unpaired if they can and still be at the same energy. So then we go 9, 10, 11, well. So this explains a couple of things. One, we can calculate the bond order. Bonding electrons minus anti-bonding electrons. So bonding electrons would be these 2, 4, 6, and 8. 8 bonding electrons. Anti-bonding electrons, 2, 4. So this tells us that we would predict the O2 molecule to have a double bond, which is the same thing that we get, the same prediction that we get from valence bond theory, and and correct also. The difference here is we also explain the fact that oxygen is paramagnetic, because in the molecular orbital diagram, we have unpaired electrons, and we would never be able to see unpaired electrons like that in a Lewis dot structure. So by constructing molecular orbitals from the atomic orbitals and filling those with electrons, we can explain the actual real phenomenon that O2 is paramagnetic.
Because it does have unpaired electrons.
Because it does have unpaired electrons, even though there's no way to see that in the Lewis structure. So that's one way that this can be more powerful. Now, in terms of you doing your homework and on the next quiz and exam and stuff, you don't have to construct molecular orbital diagrams from scratch like we just did, because we already did it. Anytime you've got sets of p orbitals combining, you're going to make those types of molecular orbitals. Anytime you've got s orbitals combining, you're going to make those types of molecular orbitals. So as long as we're not getting into the d orbitals, and we're not, that's all we ever have to do. So when you answer your homework questions about whether this is paramagnetic or what's the bond order, that kind of stuff, you can use these pre-built molecular orbital diagrams. Just remember how they go. There's one other thing that happens with these diatomics. It may come up in the homework, so I want you to be aware of that. There's a slightly different ordering depending on where you are in the periodic table. When you're looking at the diatomics from the left half of the P block, B, C, and N, you see a slightly different ordering than on the right half. The one that we did is the right half because we did oxygen, and this is also the more general one, the symmetric one. Works for lots of other molecules too. But in these cases, for these three, these two switch. They just switch position and energy. The book goes through the explanation of it. It has to do with why the orbitals are at slightly different energies for those atoms. But you don't need to know that for the exam, I don't think. It just might come in the homework. Most molecules we can explain with this type of a model. All right. So let's look at one more thing we can explain with this. And rather than construct the whole thing again, we're just going to look at a picture and talk about it, and then we'll do some problems so we can practice. So here's the NO molecule. We talked about how NO was a molecule that you couldn't really draw a good Lewis structure on because of the unpaired electrons. But you can make a molecular orbital diagram. You'll notice here, everything is the same as the orbital diagram we just did. We've still got s orbitals making sigma and sigma star. We've still got p orbitals making sigma and sigma star, pi and pi star. The only difference, you can see a little bit, is that the oxygen orbitals are a little bit lower in energy than the nitrogen orbitals. So that's because of all the stuff we've talked about, effective nuclear charge and so forth, electronegativity. So so you have a slight, down like that. This is fun.
It's really weird.
Yeah, it's ghosts, probably ghosts. But everything else stays the same. So all we need to do is fill in that different number of electrons. So we'd say NO has 11 electrons. You put them all together, fill them up, and everything works out fine with the exception of the one electron up in the pi star. But molecular orbital diagram doesn't have a problem with that. Unpaired electrons or free electrons, whatever, odd numbers of electrons, they're fine. They all work right in there. We can still calculate a bond order for NO. So we've got bonding electrons 2, 4, 6, 8, anti-bonding electrons 3. Oops, so 5 halves or 2.5. So that tells us that in the NO molecule, remember how when we were drawing it here, we were trying to decide, well, should it really be a double bond or should it be a triple bond? Well, that's kind of how it works out, that it's in between a double bond and a triple bond. And that free electron is in an anti-bonding orbital. So if we were to ionize NO, that is, get rid of an electron, we would get rid of that pi star 2p electron. We'd make NO plus, which actually is a more stable molecule, because now we have a greater bond order by taking electrons out of the anti-bonding orbitals. All right, so that's how this stuff works. So what kinds of things are you going to be responsible for knowing and answering about molecular orbital theory? There it is. Let's take a look at some of the problems in the book here. So a lot of them have to do with things like predicting the bond order. So you take your molecular orbital diagram, fill it with electrons, do the bond order calculation. Let's take a look at this one. It's kind of big. It says use the molecular orbital energy ordering for second row homonuclear diatomic molecules. That's diatomic molecules made out of the same nucleus or the same atom, which the pi 2p orbitals lie at higher energy than the sigma 2p, so that's the ones that we just did. Draw diagrams and predict the bond order in a molecule with each number of total valence electrons. Will the molecular ion be diamagnetic or paramagnetic? So all we have to do for this is draw our molecular orbitals and then fill with electrons and make these decisions. So let's do that together. We're always going to have our sigma 1s, then our sigma star 1s, or 2s, sorry, it said second row. Then we've got our pi 2p, or sorry, sigma 2p and pi 2p, pi star 2p, and sigma star 2p. That's always that same molecular orbital diagram. And now let's fill up with electrons. So I'll let you do this part. Fill that up with 10, 12, 13, or 14 electrons. Decide what is going to be the bond order for each of those, and will they be diamagnetic or paramagnetic?
MO?
Molecular orbital.
Oh, okay.
Yeah.
I thought that was like an element for a second. I was like, wait, what's that? Okay.
Yeah. No, molecular orbital. All right, so which of those four has the highest bond order? Found yet?
I see eight.
Yeah, because A is going to have the fewest electrons in anti-bonding orbitals. So let's start with that and go from there. So 10 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our bond order is going to be 8 minus 2 divided by 3, which is 3. So that should be a triple bond. Is that diamagnetic or paramagnetic? Diamagnetic. All the electrons are paired in the molecular orbitals. If we add 2 more, they go right here. So that's 12 electrons. That's the same diagram as for oxygen, O2. So our bond order becomes 2. And this is now paramagnetic because it has unpaired electrons. 13, our bond order goes down to 1.5 because we've got an extra electron in the anti-bonding orbitals. And it's still paramagnetic. 14, our bond order goes to 1. And this is now diamagnetic. That would be the molecular orbital diagram for fluorine, F2. 7 electrons each, 14 total. All the electrons are paired. So bond order of 1, single bond, and diamagnetic. All right. So that's what you need to know about molecular orbital theory. This is a really powerful technique. We're just kind of doing the basic surface treatment of it. But if you go on in chemistry or physics at all, this has really, really strong predictive power in designing materials to do what you want them to do. Like we talked about sunscreens the other day. What you would do with sunscreens is you construct the molecular orbital diagrams and you actually do computerized calculations for the energies of those orbital diagrams. And then you could predict which frequencies of light will be enough to promote electrons from lower orbitals to higher orbitals. And then you can say, okay, this molecule, we would expect this type of light can promote these electrons, and that's exactly the kind of thing we want to block. So that's what we tune to do that. Same thing with pigment chemistry, with things like solar cells, sensitizers to absorb light from the sun. You need to tune the molecular orbitals so that they absorb the right type of light. And these are the types of things you can do to do that. All right, let's stop there. It's about halfway. We'll take a break, have some more donuts. Don't have too many more. You won't feel good. And then we'll get into chapter 11, intermolecular forces. right, let's talk about intermolecular forces. So this is chapter 11. It's a pretty short chapter. We're just going to focus on this stuff, which is intermolecular forces, and then the consequences of that. So if we understand intermolecular forces, everything else, the applications of that, and those end of chapter 11 and getting into the homework should fall directly from what we know. Okay, so first, what are intermolecular forces? Anybody? Kind of mentioned them before. What does that mean? Yeah, okay. You want to give it a shot? Yeah.
I don't know, force the whole atoms together, or not, I mean like photons, neutrons.
No, quite. You're going go the other direction. So the forces that hold the atom itself together are like the proton neutron stuff. Then you've got atoms being held together, which is bonds, what we talked about in the last couple chapters. So this is then extending further out, and these are the forces that hold molecules together. These are attractive forces among molecules. So outside the molecules, how do different molecules attract each other? Grab a picture for this. Oops. Like where is it? There it is. Okay. So there's our water molecules, H2O. The bonds inside the molecules are short and strong. The intermolecular forces are the forces holding the molecules to each other. And those can change depending on temperature, of course, depending on structure, depending on various things, but they're always longer than bonds. They're always weaker than bonds. So these are not bonds. These are something else, and so they're called intermolecular forces. So they are not covalent bonds. They are longer and they are weaker. So when you boil water, what happens to the water molecules? They stay water molecules?
Yeah.
So why does it require energy to boil water? Yeah, so those are the things that are going to be broken when we change the state of a substance, either solid to liquid or liquid to gas. We're going to change the intermolecular forces. Solids have very strong intermolecular forces. Liquids, they're usually weaker. And then gases, they're non-existent or almost non-existent. So when you boil something, you are completely severing the intermolecular attraction. You're giving it so much energy that they can fly around without attracting each other. Okay, we're going to look at the different types of intermolecular forces and the types of molecules that use them, and then talk about the consequences to that. IMFs, so types of IMFs. We can split them into two categories. Although the book doesn't do that, the nonpolar forces and the polar forces. So let's look at the nonpolar one first. These are the weakest. And these are the forces among nonpolar molecules. So molecules that don't have a dipole moment, that don't have a positive and negative side, still attract each other. We can see that by things like gasoline is a liquid. if nonpolar octane molecules could never attract each other, then you couldn't have a liquid made out of nonpolar molecules. Waxes and fats are nonpolar molecules, but they're solids. So there must be some attractive forces there. And that's what we have here. They're called dispersion forces. Another name for them is induced dipole forces. What happens is this, and once again, I'm going to grab a picture because we don't need this picture. We'll get the next one. So what this is showing is a helium atom. Helium doesn't make bonds, but helium atoms can still attract each other because you can have liquid helium. Here's a helium atom. You've got the nucleus in the middle, and you've got electrons in the cloud. Remember, the electrons don't orbit. We talked about that back in chapter 7. Rather, they just occupy positions in these orbitals. And what this is showing is, like, if you could take really fast frame pictures, the electrons in these different frames would be in different spots. In the frame number 1 and frame number 2, they're on opposite sides of the atom. So there's no dipole in that helium molecule or helium atom. But in frame 3, just by chance, both electrons happen to be on the same side of the molecule. And that's going to make just an instantaneous, momentary dipole where you have a negative side on the left where the electrons are and a positive side on the right where the electrons aren't. And that just happens randomly because of the motion of the electrons. But when that happens, whoops, we have a dispersion force. So as soon as there's that instantaneous dipole, then all of a sudden, all of the other atoms or molecules around it start lining up in that same way. So one dipole, a negative and positive, can induce a dipole in the next atom, and that can induce the dipole in the next atom, and induce the dipole in the next, because that positive charge, partial positive area is going to attract the electrons that are close by, and that's going to attract the next ones, and so on. So it's going to propagate and make this, this thing that we call a dispersion force. So it's not a permanent dipole. It's not a permanent positive to negative. It's something that happens and then induces in the other molecules or the other atoms. The effect is based on the surface area of the molecules. And there's two consequences from that. One is that large molecules will have stronger intermolecular forces because they have more surface area, so the molecules can line up better and attract each other more strongly. But it also is going to depend on molecular shape. And let's look at some examples of where these two things come in. So one is just to look at the boiling points of the noble gases. Boiling points are a good indication of intermolecular forces strength because that's what you have to break to boil something. So helium has the lowest boiling point, and xenon has the highest boiling point. And that makes sense because of the size of the atom. The larger ones can have more overlap and attract each other more strongly. More electrons. That also works with the alkanes, the carbon and hydrogen molecules. So as you add a carbon and 2 hydrogens each time, you get a longer molecule, you get more surface area overlap, and you get a higher boiling point. It's almost linear. So that's that first part about how the size determines the boiling point when you're just talking about dispersion forces. The other thing is that we can look at something like this pentane versus neopentane. So these molecules both have the exact same formula and the exact same molar mass. They're both C5H12, but one has a much lower boiling point than the other. And if we think of this idea of surface area, it makes sense. The one on the left is spread out, kind of stretched out. The one on the right is more like a ball. That's the first one, N-pentane. This, the second one, neopentane, which is like a tetrahedral shape. So if you think about how those would interact with each other, one of them would have a nice large area for lots of interaction, lots of attractive forces, and the other one's like putting two balls together, not as much area for interaction. And so that's why the one has a much higher boiling point than the other. So the dispersion forces, evaluating dispersion forces is fairly simple. We're just looking for surface area, how well can molecules kind of line up, get close to each other and attract each other, and how big are they? How much can they attract each other based on their size? So that's the nonpolar dispersion forces. We should also note that all molecules experience dispersion forces. We focus on the nonpolar molecules because they don't have anything else. It's only dispersion forces. The next ones we're going to go through will have other things going on that are stronger and that are more important. All right, so let's look at the polar forces, which we call dipole-dipole forces. In this example, we have polar molecules. In the last chapter, we talked about how to determine if a molecule is polar or not. If you have a molecule, let's just say this is a molecule, that has a positive side and a negative side, then it can line up with other molecules like that, and they can attract each other. Now, those aren't going to be full charges. They're not ions. They're dipoles. So we're talking about molecules like acetone. Acetone is polar because of that CO bond. So you've got a partial negative up here, partial positive up here. So acetone molecules can attract each other by having the positives and negatives line up. Polar forces are stronger than the dispersion forces themselves. So if you look at acetone versus a similar size molecule, ethane, or I'm sorry, not acetone. Let's look at a simpler one just because they're the same size. Acetone, also, that all applies to acetone. There's nothing wrong there. But if we look at this molecule, formaldehyde, same deal. The molecular weights of these two molecules are very similar. This one's a little smaller. But the boiling points are very different. So having that polarity, even though they're the same size, having that polarity allows those formaldehyde molecules to attract each other much, much more strongly than the ethane molecules can. So let's write that. So to evaluate whether or not a molecule is going to have these types of forces, you have to be able to determine if that molecule is polar. So that's stuff we did last week when we looked at whether or not molecules are polar based on their shape and their bonds. It becomes really important in evaluating intermolecular forces. All right. Our third type of force is actually kind of a subset of dipolar forces, so maybe we'll call it 2A. It's called hydrogen bonding. This is a really confusing term because it's not bonding. It's intermolecular forces. It's not a covalent bond. But it is a really strong type of intermolecular force. So hydrogen bonding is a type of dipole force whenever you have OH and H or FH bonds. Those are the three most electronegative elements, O, N, F. So when they're connected to hydrogen, those molecules have exceptionally strong dipolar forces. Right. And we see that with things like water. So you look at a water molecule and you recognize, oh, that's a molecule that has OH bonds. So this is something that can do hydrogen bonding. And in hydrogen bonding, it's just like that picture we looked at earlier. You can take that dipole from water, and the hydrogen from one water molecule can interact with the oxygen from another water molecule and make this especially strong intermolecular force. And it's stronger for a few reasons. One, it's not just the dipole, it's actually something going on with the hydrogen orbitals. But here's the kind of effect that you get from this. So here's a graph of boiling point versus molar mass for the group 4A and group 6A hydrides, so the hydrogen compounds of those elements. As we know, in general, boiling point goes up with molar mass because of the larger dispersion forces. So that is mostly what we see in this graph, that the boiling point goes up as the molecules get bigger. But there is one huge exception here, and that's water. If we go just by molar mass, water should be down here somewhere. Right? That would fit the trend better. But instead, the boiling point is super, super high, 100 degrees, way out of line for how small of a molecule it is. And that's all due to this hydrogen bonding. So whenever we see the capability of a molecule to do hydrogen bonding, meaning that it has NH or OH bonds, then we know, okay, there's something special going on here. This molecule is going to have a much higher than expected boiling point. It's going to be much harder to pull those molecules apart. So those are the major intermolecular forces that you need to know about. And you should be able to determine whether molecules will exhibit one or more of those forces. Well, they'll all exhibit dispersion forces, but which of those forces different molecules will exhibit based on their polarity. You may need to draw Lewis structures to figure that out. It just depends. The last thing we're going to talk about, it's not as important, but it still fits in this category. Ion dipole forces. So just like dipoles can interact with each other, they can also interact with ions. This is what happens when we have ions in solution and what allows for ions to be in solution. Again, I'll grab a picture instead of trying to draw it. Oh, there we go. So if you think about what happens when NaCl goes into water, we've talked about this before when we looked at a little bit about solutions earlier. The chloride ion can be surrounded by the positive side of water molecules, which is the hydrogen side. And the sodium can be surrounded, and this would actually be in 3 dimensions, so it would be like a sphere, by the oxygen side of the water, which is negative. So in that way, ions and dipoles can interact with each other. Do you think that this interaction would be stronger or weaker than the other ones that we've seen so far?
Stronger than the first two, but not shows hydrogen bonding.
Why?
Oh, I don't know why we. I think it was. I don't know why we started hydrogen that much, but stronger than the other two because they seem to be like polar interactions.
Yeah, ionic interactions are almost always going to be polar or stronger than polar interactions, including hydrogen bonding, actually. So these are going to be the strongest types of forces. All the other things we talked about today were all partial charges. So you have a partial positive and a partial negative. And here we have something, an ion with a full charge, like an actual full charge. So that's going to be a stronger interaction. So if we were to rank the strength of these, it would be exactly in the order that we just talked about them. Dispersion forces are the weakest, followed by the dipole forces. Hydrogen bonding is stronger, and then the ion dipole forces are stronger than that even. And then even stronger than that, if we follow that trend, would be the ion-ion forces, which we call ionic bonding. So that kind of goes in a different category, but really it's the same idea. So any questions about what those forces are? Anything like that? Okay. Let's look at how we use them or what we can learn from them. And then practice a little bit of how we would predict that just based on the structures. Okay. So a couple things that this affects. Surface tension and viscosity, which are related but not the same. Surface tension is the energy required to increase the surface area. So if you have like a water droplet on a surface, how much energy is required to just kind of spread that out? How do you think intermolecular forces affect surface area? Or surface tension?
It's like a stronger force and it's less.
Close, but the opposite. The stronger force is going to make it a stronger surface tension and require more force to spread it out. I think you're on the right. Yeah. So like when you put a water droplet on a surface, you know, you can see it kind of form a droplet. You try to do that same thing with another material like acetone in the lab, it just kind of flattens out and gets the whole thing wet. And so part of that is the surface tension. It's also always affected by the interaction with the surface itself. So if you're, like we tend to think about things like polar surfaces versus non-polar surfaces, that's going to make a difference. So if you've got that water droplet on a piece of glass, which is polar, that's going to be different from that water droplet on, let's say, a table, which might be non-polar. So there can be some other things there. The other thing is viscosity. What is viscosity? I know how I define that.
Thickness of a or something like that.
Yeah, we kind of think of it as the thickness. Which is right. More correctly, it's the resistance to flow. So the resistance, something flowing through a tube or something like that. So something that we think of as very thick, like honey, right, we might say is very viscous. It has a lot of resistance to flow. How do you think that intermolecular forces relate to viscosity? Stronger forces make things more viscous or less viscous? Generally more. It is, of course, substance dependent. So like, we don't need to copy these. We can just look at them. Here's some viscosity of hydrocarbons. You know, as we add carbons, that's a nice way to look at it. So the bigger the molecules get, the more viscous it gets. Viscosity also changes with temperature. So water has this viscosity, but as you know, as you heat something up, that viscosity changes. We don't see that, or we don't notice it so much with water, but if you think about something like honey or syrup, then it really changes its viscosity pretty dramatically when you heat it up. It starts flowing more, and that's because you have more energy to stretch out or break those intermolecular interactions. Okay, so let's get into the bigger effects here. Vaporization and vapor pressure. Remember back in the gas chapter, we talked about collecting gases over water, and we said that you have to, the water has this vapor pressure that we have to correct for. Well, that pressure is caused by the intermolecular forces of water. So we need to think about our solutions a little bit differently than we might have in the past. When you think about a container of water, we just think about it as liquid water. But really what it is liquid water with some water vapor on the top of it. And let's think about molecularly why that is. We're going to go back to the gas chapter concepts a little bit here. Look at some of these curves, these distribution curves. At any given energy, which is a given temperature, even though the average kinetic energy is over to the left here, there are always going to be some molecules that have far more kinetic energy than average. And there is some amount of kinetic energy that is great enough to escape the hydrogen bonds in water. So hydrogen bonds in water have a particular energy. When those molecules get enough kinetic energy, they can escape and break those bonds. So even when you have room temperature water, let's say, most of your molecules are over to the left. They're just happy in liquid form with their hydrogen bonds. But some of the molecules are going to have enough energy to break those hydrogen bonds and get out of it. And that's what we see over on the right here. And as you raise the temperature, what do you see happening to that fraction of molecules that have enough energy needing to escape? As we go from the blue to red curve, what happens to the number of molecules that can escape? It increases. There's more. You see how the red area on the right there is larger than the blue area underneath there? So as you go up in temperature, more molecules have the necessary energy to escape. And the pressure that those molecules exert on the solution is known as the vapor pressure. See, I'm just trying to see where we can write this. Okay. The pressure that the escaped molecules exert on the solution is the vapor pressure. So when we say that something is volatile, have you heard that term before? Like volatile organic compounds or volatile solvents. What does that mean? Yeah, it means it evaporates really readily. Like something like ether or acetone or alcohol, like rubbing alcohol, when you put it on a surface, it evaporates pretty quickly. And so we call that volatile. And that means that it has a high or low vapor pressure. It's high. It's high because it means a lot of the molecules are in the vapor phase, even when some of it is in the liquid. And so how does that track with intermolecular forces then? Do you think materials with high intermolecular forces, strong forces like water, are going to generally be more or less volatile? Less, right. if they have stronger forces, then it requires more energy to escape that solvent. Whereas something with lower or weaker forces is going to be easier to escape. So things that are volatile are generally molecules like, again, ethers, like butane or pentane, those kinds of molecules that don't have strong intermolecular forces, that are mostly dispersion forces rather than things like hydrogen bonding. This also allows us to define boiling point, because if you think about that, we haven't really talked about what that is. Boiling, like what the boiling point of water is 100 degrees C. Well, what happens at 100 degrees C?
Water is liquid, gas.
Yeah, like that's how we kind of talk about it, is it starts to become a gas. But what does it mean for something to start to become gas? How do we measure that and know that exactly at 100 degrees, that's when something starts to become a gas? Yeah, it actually has to do with the vapor pressure. So we can define the boiling point in those terms. The boiling point is really when the vapor pressure equals the atmospheric pressure. So you have atmosphere pushing down on your water, pushing those molecules back down into solution. Once they get so much energy that there's enough up there that the vapor pressure is the same as the atmospheric pressure, then the vapor can escape into the atmosphere and it's no longer held down into the solution. So that's why boiling point changes with different atmospheric pressure. Like if you go up in the mountains, has anybody tried to boil water in the mountains? Yeah, it's not about longer or quicker so much as that's another issue. There's less atmospheric pressure, so it doesn't get as hot. So a lot of times on packages, it'll say like high altitude cooking directions for food, and that's because the water won't get as hot before it starts boiling as it does down at sea level. So you have to correct for that. And so we can make graphs like this. And we can find the boiling point based on this kind of idea. So here, you've got the vapor pressure on the left, on the y-axis, and the temperature on the x-axis for some different materials, some different solvents. The steeper that curve is, the lower the temperature before the boiling point and the vapor pressure are equal. And that line, the normal boiling point, is when the vapor pressure equals atmospheric pressure, which is defined as 760 torr for the normal boiling point. So where those curves interact is the boiling point. And different materials are going to have slightly different curves, different behavior, which you can see here, some different kinds of slopes. But you can determine what the boiling point is going to be at any given atmospheric pressure based on this idea. All right, any questions about that? So we know about boiling. We know about intermolecular forces now. Let's look at what's happening with water. As we heat it up. Oops. So as you boil water, you have this kind of behavior. We call this a heating curve. We're heating the water up, and then the temperature is changing. So normal, regular liquid water, you add heat, the temperature goes up. Makes sense, right? You heat it up, temperature goes up. But when it gets to the boiling point, you add heat and the temperature doesn't change. So what's happening to that heat? Why are you adding heat at 100 degrees and the temperature is not changing at the boiling point? What is that heat doing instead? Not causing the temperature to change. Yeah, right. That heat is going to breaking those intermolecular forces, breaking those hydrogen bonds. So the temperature doesn't change, but the water is still absorbing heat to break those hydrogen bonds. And the same thing happens when it's melting. So if we put that all together, we have this. Which we call a heating curve for water. It's a graph of water being heated from one temperature to another and looking at the temperature versus the amount of heat that's being added. And we can learn things from all aspects of this graph, from the slopes, from how long the different segments are. All of that stuff tells us about the intermolecular forces and about what's going on. So let's start at the beginning and go through each step and see what's happening here. We're starting at minus 25 degrees when water is in what state? It's solid, it's ice. So you heat up the ice and get to 0. And we have our first phase change. That's the number 2 labeled there. What's happening right there? It's melting. What does that mean? Yeah, it's changing states, turning into a liquid. So the water molecules the intermolecular forces are stretching out a little bit, becoming a little bit weaker. If we look at the actual structures, we have this rigid ice structure here, and then we start getting to this amorphous, non-ordered liquid structure until we're all the way to liquid at the end of all that energy being put in. So then 3, we are heating that water up from 0 to 100. And then we've got our boiling point, which we just talked about. So let's look at the relative sizes of these lines. It takes about, let's see, that's kilojoules per mole. So I'm guessing, looking at that, it's a little less than 10 kilojoules per mole. Yeah, 7.5, it says up there. To heat liquid water from 0 to 100 degrees. That's how much energy it takes. Then it takes 40.7 kilojoules per mole to boil it without changing its temperature. So look at the difference in those two numbers. Takes 5 times the amount of energy to break up those intermolecular forces as it does to heat the water up. So like when you boil water on the stove, most of that energy is actually going into the boiling, not the heating. It heats up relatively fast. Takes relatively little energy to heat up. And then once you hit steam, then you can warm up the steam, to whatever temperature. So what else can we learn from this plot? Well, we can look at the slopes of the heating curves. What does it mean that the ice slope is steeper than the water slope? What does that tell us about the ability of these things to absorb energy and heat up? Well, which one heats up faster with the same amount of energy? Ice or water? Ice, yeah, because the slope is steeper. So if you put the same amount of energy in to ice and to water, the ice will change temperature more than the water. And that's called the specific heat, or the heat capacity. So there's our heating curve. How would you expect this to change for a molecule that had weaker intermolecular forces? Heat up faster, or what? Maybe steeper slopes. We don't know. Well, the slopes may not change as much, it's those flat areas that are going to change significantly. Something with weaker intermolecular forces is going to have a much shorter number 4 line there because it's going to be able to be boiled with much less energy. So that's how that can affect intermolecular forces. And I think the last thing we want to look at here is the phase diagrams, which you've probably seen before. We can look at a phase diagram for water. This is not to scale, because the actual one kind of looks a lot different. Here's when we graph pressure versus temperature. Have you seen these things before? Some people not, maybe. Okay. Well, we're graphing pressure versus temperature and looking at the different states in different parts of or different regions of the graph. So they've given us some nice kind of landmarks here that we know about. Standard temperature and pressure, 760 torr and 0 degrees C, would be right here. And that's right at the point where water or ice turns into water or water turns into ice. So that's called the fusion curve, because liquid freezing into ice is called fusion. The energy is called the heat of fusion. The other direction is called melting. Another landmark here is at atmospheric pressure and 100 degrees C, you would expect liquid water to turn into a gas. And so that's what we call the vaporization curve, where liquid becomes gas. And what we can think about with these phase diagrams is what happens when we travel in different directions on this phase diagram. So we could say, all right, let's have water at 50 degrees C, and let's lower the pressure by some amount. What happens when we lower the pressure by like that amount? Well, it's going to boil. So even though we haven't changed the temperature, if we lower the pressure by that amount, we cross over the vaporization curve, and so we boil the water. If we're going in this direction, same thing. We cross the vaporization curve, so if we heat the water up at the same pressure, we expect to boil it. We can also look at some of these other regions in the curve. Like if we're at solid water way down here at really, really low pressure, we've got ice at really, really low pressure and really, really low temperature. If we heat up down there, we actually miss the liquid entirely, and we sublime and go directly to the gas. So ice will become a gas without becoming a liquid first when we're at extremely low pressure. Again, this isn't to scale. It's actually like, it looks kind of different to scale. So it's not as close to normal conditions as it looks. And then right in the middle here, you've got this triple point. That's the point at which solid, liquid, and gas all exist simultaneously. So if you're at that particular pressure and temperature, you will have, and it's a pretty low pressure, you will have liquid, solid, and vapor water. And then as you exceed the critical point up here, either by pressure or by temperature, so this is at high pressures, extremely high pressures, and high temperatures, you create a new state of matter called a supercritical fluid, which kind of has properties of a liquid and a gas. And this can be really useful for various applications. One of them is supercritical CO2 is a pretty nice solvent, and it's really green, meaning that it doesn't affect, it's not really bad for the environment because it's just CO2. So what you can do is you can make supercritical CO2, use that as a solvent. One application for that is taking caffeine out of coffee to make decaffeinated coffee. You can dissolve the caffeine in the supercritical fluid and then just let the CO2 evaporate or recapture it to use again in the next round. So that's a supercritical fluid, and that's always kind of at the top right end of a phase diagram. So let's look at some problems in these topics. Oh no, my subscription has expired. Okay. So I need to log in again here. We went through a lot of information. Let's look at how that translates into questions and problems that we can do. If it lets us. There it goes. So one way that we can use these ideas is in a problem like this. For each pair of compounds, pick the one with the higher boiling point. Explain your reason. So let's look just at A right now. Everybody, it's like basically a true-false question, right? You got 50-50 chance of getting it. Everybody think about those two molecules and pick which one is going to be the higher boiling point. And then, well, and as part of that, think about why you picked that. And we'll see what we're thinking. Why would one of those have a higher boiling point than the other? How could you figure that out? Everybody got one? All right. How many people say the first one is the higher boiling point? How many people say the second one is the higher boiling point? Wait, I thought everybody got one. Let's try again. Everybody pick one. How many people say the first one is the higher boiling point? How many people say the second one is a higher boiling point? We still didn't get everybody. Let's try one more time. Still thinking? Give me another minute to think about it. You can just go along with the crowd if you want. But you might all be wrong. Do you want to say something? Oh, no.
Sure. The first one.
You went with the first one? Okay, so how many people are going with the first one now? How many people are going with the second one? Oh, everybody just joined the crowd. All right, does anybody want to offer a reason why you picked the first one? Yeah. Yeah, that one's capable of hydrogen bonding. Is that what you're going to say too? Yeah. That first one's capable of hydrogen bonding because it has that oxygen hydrogen bond in it. And the second one is not. So that's going to make that first one a much higher boiling point, stronger forces. Okay, what about the second one, B? What do you think about that one? You got CH3OCH3 or CH3CH2OH. Okay. Many people say the first one has the higher boiling point. Second one? Oh, okay. Pretty good agreement here. So why the second one? Same reason? Yeah, these are isomers. These are made out of the same atoms. But in the first one, that oxygen is sandwiched between two carbons, whereas in the second one, it's on the end with an OH. So for hydrogen bonding, we need that OH. It's not just enough to have the oxygen, but it's the oxygen connected to the hydrogen. So we would expect that to have much higher boiling point. Same thing here. So H bonding, not bonding. Okay. And then what about C? Which of those two is going to have the higher boiling point? Everybody take a look. First one? Second one? Okay, why the second one? More mass, more size? Yep. So that's, in this case, they both have the same type of intermolecular forces, which is what? What type of forces there? Remember what that's called? Yeah, the dispersion forces. So when you have the same type of forces in two different molecules, then whichever one is bigger is going to give you the higher boiling point generally, have the stronger forces. So A, B were examples where we had different types of forces that we were weighing. C, same type of forces. All right, so that's one way we can look at these. There, as you can see here, there's a whole bunch of practice problems of the same type. We can also think about how these things are going to combine together based on these forces. Take a look at this one. Determine whether the pairs form a homogeneous solution or would they separate? They form heterogeneous solutions. How can we figure that out? How would you? Based on the strength of the forces, but also the similarities of the forces. So if you think about what it takes to make a solution, you have to take two pure substances, you have to break up their individual intermolecular forces, and then put them together with new intermolecular forces between the two substances. So if the pure substances bind very strongly together, but have very different forces from each other, then they're not going to want to come together. So it's not just the strength of the forces, it's also the compatibility of the forces, we might say, or how they can they actually fit together and interact with each other. So look at that first one, A, CCl4, carbon tetrachloride, and water. Would those two form a homogeneous solution or a heterogeneous solution, or a heterogeneous mixture? Would they combine together in solution, or would they stay separate? What do you think? How many people say these would combine together in a homogeneous solution? Stay separate? Why stay separate? It's like a couple of you. Just a guess? Yeah, they have different types of forces. What's the type of force in CCl4? Anybody? It looks like it should be dipolar because C and Cl make polar bonds. But in that molecule, remember it's tetrahedral, which means all those dipoles are going to cancel each other out. So CCl4 is actually a nonpolar molecule. So that's going to hold together primarily by dispersion forces. And of course, water, we know, is polar and hydrogen bonding and dipolar forces, that kind of stuff. So those would likely not mix, not form a solution because of their different types of forces. All right. What about, let's jump down to C since we're still talking about this molecule. Br2 and CCl4, would that form a solution? So what do you have to ask yourself to figure out if those are going to form a solution or not? We have to decide, we already decided that CCl4 is nonpolar and attracts it to itself with dispersion forces. So then we have to say, is bromine, Br2, also nonpolar, also controlled by dispersion forces? Is it? Or is it polar? It's not polar, right? Br and Br, there can't be any polarity between that because you've got the same element on both sides of a bond. There's not going to be a negative and positive side. So those, we would expect they would form a homogeneous solution because they interact with the same types of forces. All right, let's jump back up to B. KCl and H2O. Now you might know this just from experience. Are those two going to make a homogeneous solution? Potassium chloride and water? See some head nods. Yeah, they are. It's like salt and water, right? But just potassium. So we know that's soluble. How can we talk about that in terms of forces?
Strong.
They do, but the KCl, what types of forces are in KCl? Well, those are just actually pure ionic forces. They're ionic bonds in the pure substance. But you're right, when KCl and H2O combine, you're going to have ion dipole forces between the ions and in KCl and the dipole in the water. So that's one reason water is a really good solvent, is it can interact well with ions. And you can make these ion dipole forces and make these homogeneous solutions. Now that, of course, there's some like other stuff that we know about now that are issues, like our insoluble ions. Remember the solubility chart as we're getting ready to prepare for the final? Like copper hydroxide is not soluble. But that's ionic, right? So it should have the same types of forces. So what's going on there? If we still have ions and we still have dipoles, why is KCl soluble but copper hydroxide is not? No, not quite. We actually have to go back to some earlier concepts to talk about this one. Remember that mixtures are about balancing energies. It's about balancing the energy between the pure substances and when you put them together. So in an insoluble salt like copper hydroxide, the forces holding the copper and the hydroxide together are so strong that water is not going to be able to get in there and break it up and have its own. So like the good forces that you'd form between the ions and dipoles aren't enough to overcome the strong forces of that ionic compound. So that has to do with the lattice energy and some of the other stuff that we talked about in an earlier chapter. Okay, let's look down at D then. Ethanol and water. Are those soluble? Do those mix together? Yes, no? No? Has anybody experienced ethanol mixed with water? No? Well, how can we think about this one?
It can't mix. It's just like one's on top of the other.
One's going to be on top of each other, not the other?
Yeah.
Based on density?
One's an alcohol.
Yeah, but is density what controls whether things will mix or not?
Water can't break up that intermolecular forces at all.
What kinds of intermolecular forces are in ethanol?
Or you have hydrogen power.
Yeah, it's got that OH, so it can do hydrogen bonding. And what kind of intermolecular forces are in water? Yeah, but also hydrogen bonding from the OHs. So those have the same types of forces. So we would expect they would mix. You've got ethanol, and it's true that because so you can try this. You can actually layer ethanol on top of water because it has a lower density. So if you're very, very careful, you can take some ethanol in a thin tube, and you can very slowly with a pipette just barely put it over the side and carefully layer it, and you will form two layers. But if you disturb it a little bit, it'll all just mix up and become homogeneous. Because there is a slight difference between those forces, but because they both have hydrogen bonds, they ultimately can mix and keep each other stable. So those would mix together. They have the same types of forces. All right. So all of these calculation ones that you see in the homework here, if you're going through the book, we're not doing that part of this chapter. They shouldn't be in the Mastering Chemistry. There's a type of equation that you can use to do some calculations with the vapor pressure and stuff. We're not doing that. So you can skip over all those. We just care about the qualitative part of this chapter, like the explaining things. Let's look at how we read things from a phase diagram. That'll be about it for us today. We're going to look at a phase diagram for iodine. All right, there's our phase diagram for iodine. What is the boiling point? Just based on that phase diagram. So the way to do this is look at the phase diagram and identify the different states of matter. They're always going to be in the same place. You're never going to have liquid at colder temperatures than the solid overall. So, does everybody see the three sections of this phase diagram? What's going to be the part over here? Yeah, that's always going to be your solid because, and if you ever forget or get confused about this, think about where that is in the units. So really, really low temperature, medium to high pressure, that's probably going to be a solid. All right, really, really low temperatures is usually solid. So then what's this other one underneath over here? That's going to be the gas, the one that's at the really highest, the lowest pressures at the highest temperatures. And then that leaves the liquid right in the middle here. And most phase diagrams are going to look like that. We should also note, and you'll be able to do some practice in the homework here, phase diagrams don't have to be just between solid, liquid, and gas. You can have different types of solids, different phases of liquids that are in this phase diagram. Like with ice, there are a bunch of different types of ice depending on pressure and temperature. And so you can have a phase diagram of the different types of ice too. But our typical ones are between these three states. So now that we've labeled those, what's the boiling point and how can we find that? Yeah, how'd you know that was the boiling point?
It goes from solid to gas. Doesn't like skip.
Yeah. So the point at which it goes from liquid to gas is what we call the boiling point at one atmosphere, the normal boiling point. So right where it crosses that liquid to gas line, that vaporization line, is at 184.4 in this particular phase diagram. So we would say that the boiling point is 184.4. What's the melting point at the same pressure? Yeah, that's going to be that other number there, 113.6, where we cross from the solid to liquid. Everybody see that? That barrier between solid and liquid. What state is present at room temperature and normal atmospheric pressure? So what's room temperature? Approximately in Celsius. You know? Say 90? 40 now? No. Yeah, it's like between 20 and 25 generally is room temperature. Yeah. 90 would be a hot room, like almost boiling water. Okay, so if we're about like 20 to 25 degrees C and normal atmospheric pressure, what state are we going to be in? Solid, yeah, because you're to the left of that line at 113, because you're way below that, on that 1 atmosphere line puts us in the solid area. And then which state is present at 186 degrees C and 1 atmosphere? It's a gas. It's just to the right of that boiling point line. So that means we're going to have a gas at temperature. Yeah.
This is like probably a dumb question, but why? Like to me, it looks like it goes from like solid to gas to liquid.
Yep.
Instead of like solid to liquid to gas.
Well, it depends where you are and what you're doing. So if our pressure is 1 atmosphere and we heat this thing up, we go from solid to liquid and then to gas. See that? At 1 atmosphere. But if we're at low temperature, like down here, or low pressure down here, we go directly from solid to gas and we don't get to be a liquid. If we think instead about staying at the same pressure, or staying at the same temperature, so we're at like 120 or something over here, and we increase the pressure, we can get the gas to the liquid, but we keep increasing the pressure, and according to this phase diagram, we'll never make it to the solid because we won't ever cross over that liquid to solid line. So we have to lower the temperature to get to the solid. Does that help?
Yeah.
Okay. Other questions about phase diagrams? All right, we got about 15 minutes left. So if you've got any other questions about homework, chapter 10 homework's due tomorrow, and then it'll be our last week of class. So lab Monday, chapter 12 on Tuesday, quiz and review on Wednesday, final exam on Thursday. Have a good weekend.
Thanks for the donuts.
Oh yeah, grab more donuts on your way out. Bring them to somebody at your house or something. I don't know. I don't need that many donuts.
Look you up the meme.